In this next video, we're going to finish chapter 10. In particular, we're going to prove the formula for order of the power of an element, and we're going to also look at the relationship between the order of two different elements, A and B, and the order of their product, AB. This is the theorem that I asked you to try to figure out for yourself what the formula would be. If I have a group and an element of the group of finite order n, then I can compute the order of any power of that element, and it will simply be the ratio of n, the order of A, and the greatest common divisor of the order of A and the exponent k. Before we move on, there are a few number theory results that I want to remind you of because they'll be used in this proof. The first one we proved in class: if I have an integer that is a factor of a product of two integers, and if the integer a, the divisor, is relatively prime to one of those two factors, in this case b, then a, the divisor, must be in fact a divisor of c. So if a divides bc but is relatively prime to b, it is a factor of c. The next result is not one that we proved, but it's easy enough to convince yourself of its truth. If I take two positive integers and I divide each by the GCD of the pair, then the resulting integers, notice that when I take a over the GCD of AB, I do get an integer because I've divided a by a factor. B over the GCD of AB is an integer. And because I've removed from both a and b any common factors, the resulting ratios must be relatively prime. We take away all common factors, the remaining factors are relatively prime. And the final result is that if I have a pair of positive integers, and if each is the divisor of the other, then they must be equal. It is essential that they be positive because you can imagine that if I look at minus b and b, then minus b is a factor of b is a factor of minus b, but b is not equal to minus b. On the other hand, if we require them both to be positive, that situation can't arise, and I encourage you to prove for yourself that if a divides b and b divides a, then a and b are equal. Let's move on to the proof of our formula and give a name m to the order of a to the k. We're interested in showing that m is n over the GCD of n and k. So first thing we're going to do is we're going to take a to the k and we're going to raise it to the power of the GCD of n and k. If the only way for the order of a to k to be this ratio is if I take a to the k, raise it to that power, I get e. That's at least a necessary condition. It's not sufficient, but it is necessary. So let's verify. Using my laws of exponents, when I take this expression here, I can rewrite it like this. I can exchange the rules of n and k just using my properties of exponents. A to the n, on the other hand, because the order of a was n, a to the n is e to any power is e. So I've verified that if I take a to the k, I raise it to this power, n over the GCD of n and k, I get the identity. As I said, that is not a guarantee that n over GCD of nk is the order of a to the k. However, using our previous result, it does tell us that the order of a to the k is a factor of that ratio. What we need to show is that they're actually equal. In order to do that, let's look at what we know about order of a to the k. I know that if I take a to the k to that power, I get e. So that tells me that a to the power km is the identity. Now, n is the order of a, and using our previous result again, the order of a divides any exponent of a that gives me the identity. So n divides k times m. Just writing out what that means in terms of an equality, it says there's some integer q such that nq is k times m. I write it in this form because what that allows me to do is to divide both sides by some factor, which in this case is going to be the greatest common divisor of n and k. That gives me this expression here, n over the GCD of n and k, which is an integer, times q, is k over the GCD of n and k, another integer, times m. Writing this in terms of this divisibility, it says that n over the GCD of nk is a factor of this product. Now, as we observed in the previous slide, these two integers, n over the GCD and k over the GCD, have no common factors. And so using our third result, I can conclude that n over the GCD of nk divides this other factor, m. These two guys have no common factors, therefore this n over GCD of k and n is a factor of m. So up here we showed that m is a factor of the ratio. Now we show that ratio is a factor of m. Using our third result, we conclude that this ratio, n over the GCD of n and k, is m. M is the order of a to the k, and that proves the result that we were hoping to prove. The one you did in part 1. Just observe, when I take a to the 0, I apply my formula. I'm dividing by the GCD of 12 and 0. Well, as you remember, the GCD of 12 and 0 is the greatest common divisor of both 12 and 0. Well, the greatest divisor of 12 is 12, and every positive integer is a divisor of 0. So when we're looking at the common divisors, the greatest common divisor will be 12. As I go through the rest of them, it's pretty clear that my formula applies, just verifying what we saw earlier. Notice here the two elements that we got of order 12, a to the 5th and a to the 7th, they're of order 12 because the GCD of 12 and 5 is 1. The GCD of 12 and 7 is 1. So these two guys of order 12 means they're also generators of my group. I had a cyclic group generated by A, also generated by a to the 5th and a to the 7th. Here's an exercise for you to do. Take a group G, which is the cyclic group of order 35. Find the order of a to the 14th in that group, and then do the same for this group of order 30, but now this is an additive group. So again, make sure that you translate what it means to be a power in a multiplicative group into the corresponding result for an additive group, and then you can apply the same theorem. Try it for yourself, and then when you have finished, come back to the video and we'll go over the answers. First one is straightforward. You just apply the formula. Order of A was 35. It was the generator of that cyclic group of order 35. And 14 is the exponent. The GCD of 14 and 35 is 7, so the order of A to the 14th is 5. Verify it by taking a to the 14th, a to the 14th squared, cubed, and 4th. You're going to find none of those is the identity. A to the 14th to the 5th power is identity. For the second one, we want to move into additive notation. When I was in multiplicative notation, I was taking powers of A. In an additive group, powers of A become translated into multiples of A. So I'm interested now in the relationship between the order of k times A and the order of A. And the same result applies. I just changed the format, but I haven't changed the outcome. So if B is k times A, the order of B is n over the GCD of n and k. For our particular group, I choose any generator I want, but 1's the easiest one. Order of 1 is 30. 18 is 18 times 1. And so applying the formula, I see the order of 18 is 30, order of 1, over the GCD of 30 and 18, which is 6. So I get an element of order 5. 18 has order 5 in integers mod 30. Again, you can verify that by taking 18 times 1, 18 times 2, 18 times 3, 18 times 4. Those will not give you 0, which is the identity, but 18 times 5 will. Another sort of big topic, and that is the relationship between the order of two elements and the order of their product. In this theorem, there's a very nice relationship between the order of A, B, and the order of AB. But I want to emphasize that this occurs in a very narrow setting. In this setting, I have a group. I have two elements, both of finite order. Order of A is M, order of B is N. But I'm assuming that M and N are relatively prime. That's not going to be true in general. I'm assuming further that A and B commute. And when I have that situation, two elements of finite order, and the orders are relatively prime, and the elements commute, then the order of the product is the product of the orders. This is not true in general. It is only true in this particular setting. Let's see why it works. I take two elements that commute, and I assume that they have relatively prime orders. I want to show that the order of the product is the product of the order, so as usual, I start by taking AB, raise it to the mn power. Here again, I'm using the fact that they commute, using the properties of exponents, and now I use the fact that A to the m is the identity, since m was the order of A, B to the m is the identity, since n is the order of B. So check off my first condition. If I take AB to the mn, I get the identity. What does that tell you? It tells you the order of AB is a factor of mn. In the interest of space, we're going to finish the proof on the next slide. What remains to be shown is that this product of the orders is a factor of the order of the product. Once we've proven this, then we'll have our result. So let's let the order of AB be k, and as usual, I can immediately say that AB to the k is the identity. Using the fact that A and B commute, A to the k, B to the k is identity. And so I can say that A to the k is the inverse of B to the k. This tells me that A to the k and B to the k have the same order. They have the same order because they're inverses of each other. I also know what their orders are. I know the order of A to the k is the order of A over the GCD of m and k. The order of B to the k is the order of B over the GCD of m and k. Well, if I think about what that means, this is an integer, and it's a factor of m. This is an integer. It's a factor of n. And these two integers are equal to each other. That's what we saw here. So that makes them a common factor. This is one integer is a factor of both m and n. It is a common factor of m and n. M and n have no common factors other than 1. That was the fact we were given, that they were relatively prime. And what that means is that these ratios, m over the GCD and n over the GCD, are both 1. How could they be 1? Well, the only way that could happen is if the GCD of m and k is m, and the GCD of n and k is n. What does that mean? That means that m is a multiple of k, right? Greatest common divisor of m and k is m. M is a divisor of both of these. M is a divisor in particular of k. N is a divisor of k as well. So both m and n divide k. In general, what I can conclude from that, if I have a common divisor, then what I can say is that the least common multiple of m and k, right, is going to be a divisor of mn. Or rather, I'm sorry, the least common multiple of m and n is a divisor of k. In the situation when I have m and n relatively prime, their least common multiple is their product. So I know that if m divides k and n divides k, I know that the product mn divides k. Again, because they are relatively prime, I can conclude this. In general, the best I could say is that their least common multiple is a factor. And this was what we wanted to show. We showed in the previous slide that k was a factor of mn. Now we show that mn is a factor of k, k being the order of the product, AB. And therefore, the order of AB is mn, which is the product of order of A and order of B. So in the narrow setting, when order of A and B are relatively prime, then the order of A times B is the product. Oh, and don't forget, A and B must commute. Then the order of AB is the product of the orders of A and the order of B. Very important point. that I want to make here is that when we talked about the order of cycles in the symmetric group, we proved that when we have disjoint cycles, and I looked at the order of their product, I concluded that the order of the product, sigma tau, was the least common multiple of the order of sigma and the order of tau. That is not true in general. It is true in the symmetric group, but not in the general group. In the symmetric group, we had a very strong property of disjoint cycles, and that was that if I have a product of disjoint cycles and power k gives me the identity, then each of those individually, when raised to the kth power, gives me the identity. That was a homework problem that you did. That's not true in general. In general, if I have commuting elements, the fact that ab to the k is identity does not tell me a to the k is identity, nor does it tell me b to the k is identity, but it does tell me that a to the k and b to the k have the same order. That's all I can deduce from that. And so I don't get the stronger result, which means that I cannot conclude that the least common multiple of the orders of sigma and tau is the order of the product sigma tau. In a general group, if m and n are not relatively prime, there's no formula that will tell me what the order of AB is as a function of the order of A and the order of B, even when I know that A and B commute. The best I can do is to say that if I have two elements of finite order and they commute, then the order of the product is a factor, is a divisor of the least common multiple of the two orders. I don't know which divisor it is, I just know it's some divisor. Here's an example to illustrate that. Suppose I take an element of order m and call it, well, take an element A of order m and let B be its inverse. I know that the order of B is m. Therefore, the least common multiple of their orders is the least common multiple of m and m. That's, of course, m. But when I multiply A times B, I get the identity, so the order is 1. So here's an example where the order of the product is a divisor of the least common multiple of the orders, but is not equal to it when m is not 1. Another example, suppose I take order of A is 24. I choose B to be A squared. Well, I know the order of B in that case. The order of B is order of A squared, which using my formula from before, it is 12. So if I look at the least common multiple of the orders of A and B, it's the least common multiple of 24 and 12. Least common multiple of those two integers is 24. But when I compute the order of A times B, that's the order of A cubed. And the order of A cubed, using my formula, is 8. So the least common multiple of order A and order B is 24, but the order of AB is 8, a divisor of 24, but not equal to 24. So that A and B commute, things get even worse. When they commute, I can at least say that the order of AB is a factor of the least common multiple of the orders of A and B. When they don't commute, I can't even say that. There is really no relationship at all between the order of A, the order of B, and the order of AB when A and B don't commute. Here's an example to illustrate it. We're working in S6, and I want to find the order of each of these products, a product of a 2-cycle and a 4-cycle in S6. Take a minute and compute those, find the orders, and then we'll come back to the video and we'll talk about it. In the first case, I have a 2-cycle and a 4-cycle that are not disjoint. So the best way to proceed is just go ahead and compute the product. The product is a 5-cycle, so the order is 5. Product of a 2-cycle and a 4-cycle gives me an element of order 5. The second example, I did have disjoint cycles, so I know from previous work that the order of the product is the least common multiple of the order of the 2 cycles. That has order 2, that has order 4, least common multiple is 4. So this is a case where I have commuting elements. In the previous case, they didn't commute. These cases, they commute, so I do know at least that the order is a divisor of the least common multiple. In this case, again, two cycles that are not disjoint. When I multiply them, I get a 3 cycle. So here you see I have 2 cycle, a 4 cycle, product is a 3 cycle. So an element of order 2 multiplied by an element of order 4 gives me an element of order 3. Up here, element of 2 times an element of order 4 gave me an element of order 5. So when I don't have commuting elements, I can see absolutely no relationship between the order of each individual element and the order of the product. This is just an illustration to make sure that you don't take the specific result that's true in Sn or true for commuting elements whose orders are relatively prime and try to apply it in a setting where those hypotheses don't hold.